Okay, so let's begin. So today we're just going to do the application to everything that we have done so far in the early universe to inflation. So I'll just begin with a short introduction. Then we'll spend some time on inflationary dynamics and so-called slow roll parameters, which play an important role. And then I'll introduce the Bunch-Davies vacuum. So basically, we saw last time that in quantum field theory in curved spacetimes, we don't have enough symmetries to single out a single vacuum state. We're going to time-dependent geometry. But we also saw last time that in the de Sitter case, in the spacetime where background spacetime where de Sitter, then in fact we do have enough symmetries to single out a unique state. And this is a state that is going to be used with some slight modification in inflation. And then we'll talk about how one can theoretically compute power spectrum and how one then experimentally, what one may have experimental measures and what one compares with. And then finally, the successes and limitations of inflation. Okay, so we did very early universe, we did this introduction. It was really including quantum field theory in curved space-time, and we also done the introduction to cosmological perturbation theory, and then again elements of quantum field theory in curved space-times, and now that is where we are going to start out today. Okay, so as I explained in the very first lectures on the early universe, the very early universe provides a natural arena to test quantum gravity. In particular, it provides guidance for formulating in detail the theoretical framework and to compare the theoretical ideas with observations. Now, the standard tools that are used currently, they are really Friedmann-Lemaitre Robertson-Walker solutions with Einstein's equations and quantum field theory of linear perturbations, linear cosmological perturbations, ignoring the back reaction. So we assume that these fluctuations have very low energy, so they don't really affect the background dynamics. And then one can check that this is self-consistent by looking at what happens in the early universe. In other words, one makes this assumption, finds some solutions, looks at the quantum fields which are propagating, and then checks that during inflation, in fact, the stress energy tensor in this perturbation is completely negligible to the background stress energy tensor, and so we can ignore it. And the leading paradigm for this exploration is in general relativity era. That is to say, when the curvature and matter densities are well below Planck scale. We're going to see much more detail to this lecture. I mean, not much more detail, but in some detail. That in fact, at the inflation level, the space-time curvature is about 10 to the minus 12 times the Planck curvature. Which is about Planck length to the minus 2. And so this is a huge factor, and therefore, one can ignore what is happening to the space-time curvature. The effect of the quantum gravity corrections during inflation. So the point here is really, this is really for future. The inflation provides for us a nice guidance for future opportunities. Can we extend this scenario to this Planck regime, and can we do something? Unfortunately, we don't have time to cover that part, so we'll just stop at the inflation itself. So here is the main idea now. So I'll be slow, and please stop me anytime something is not clear, because this really is a crystallization of the main assumptions that underlie inflation. You hear a lot about inflation, but you would like to know what exactly is one assuming. So this is what is needed up here. So let me first talk about the minimal assumptions and then talk about the major success. So the assumptions are that sometime in the early history, the universe underwent a phase of accelerated expansion during which the Hubble parameter, remember the Hubble parameter is just A dot over A is a proper time, dot is a proper time derivative, sorry, dot is a proper derivative instead of proper time. So this is nearly constant. And if this was nearly constant, then clearly the A of t will go like e to the h naught t. just solving that equation up here. So if there is a nearly exponential expansion up here in the very early part of the universe, then starting from this phase until about the cosmic microwave background era, remember that the cosmic microwave background era is really much later, about 380,000 years later, right? This is really very early, very, very early. If you assume classical general relativity, then it's really very close to the Big Bang, whereas the CMB era starts at 380,000 years, much later. So starting from this, at the end of inflation, up to the cosmic microwave background era, one assumes that the universe is well described by the Friedmann-Lemaitre-Robertson-Walker background with linear perturbations. So this is what we have been doing. Then you've got a background space-time. It is during inflation, it is sourced just by the scalar field, the potential, that is the inflaton. And then the only matter is, like as I said, inflaton with the suitable potential. And then on the onset of the slow roll phase of inflation, this is the important point, the Fourier modes of quantum fields describing the perturbations were in the Bunch-Davies vacuum. So first let me explain this. So the idea is that during inflation, we've got a nearly exponential expansion. As we'll see, it's not exactly exponential, but nearly exponential expansion. Therefore, the space-time geometry is kind of well approximated, not exactly, but is well approximated by de Sitter space-time. Now in de Sitter space-time, we saw at the end of last lecture, there is a preferred vacuum state. This is the Bunch-Davies vacuum state. It's a regular adiabatic order 4, actually much higher. It's a Hadamard state, which is actually it's a regular state, which has a property that the 2-point functions are all de Sitter invariant. So that is a state which we assume. So the idea is that the universe undergoes a very rapid expansion. As I told you, if it is about 60 e-folds, then a hydrogen atom gets expanded to the size of a galaxy. So it's really, really quite astonishing. And the amount of time it takes for this is about 10 million Planck second. Now Planck second is 10 to the minus 43 seconds. So 10 million Planck second is still a very, very, it's 10 to the minus 33 seconds. So it's a very small amount of time. So the idea is that and this is all consistent with classical general relativity. It's not obvious that it should be consistent, but it's all consistent with classical general relativity without the curvature becoming very large. So you got this very rapid expansion that happened in the early universe. And in the beginning, since the expansion is nearly exponential, the idea is that we say that we got this quantum cosmological perturbations, right? The idea is that you've got a background space-time, which is Friedmann-Lemaitre-Robertson-Walker space-time, but then there are cosmological perturbations. We treat them as quantum fields, and we assume that they are in the vacuum state. So they are as little excited in some sense as possible. But which vacuum state? Well, it is a vacuum state which is compatible with the de Sitter invariance up here. So starting from this phase until the CMB era, at the onset of slow roll inflation, the quantum fields are in the Bunch-Davies vacuum. But actually, as far as observations are concerned, we don't have to worry about all Fourier modes. Because in the Fourier expansion, we got modes starting from k equal to 0 to k equal to infinity. We got all these expansions. But because we are here, this is time saying we are here, we look back our light cone, and that light cone will intersect the CMB surface somewhere, and that is the only thing that is really available to us for observations. What is outside that is not available to us with observations. Therefore, there is a limit. So extremely long wavelength modes are not observed. There is an upper limit on the wavelength of the mode. Also, what we are interested here is in cosmological perturbations. In other words, when the universe began, it had these cosmological perturbations which really, there were no stars, there were no galaxies, there was nothing like that. So these were kind of primordial fluctuations that were there. And the idea is that these fluctuations grew to become, galaxies, stars, and this large-scale structure evolved from them. Of course, once this structure evolves, then astrophysics takes over. But clearly, what is happening in the solar system is not dictated by complete cosmological considerations. Sun is over there, sun is not over there, there are only so many planets, and so on and so forth. So on kiloparsec scales, what we observe is not going to be traced back to cosmology. It is only kind of megaparsec to gigaparsec scale. That is to say, about 300,000 light years to 3 million light years to 3 billion light year radii. Those are going to be explained by cosmological scale. So we're going to small wavelength cutoff because of astrophysical effects, which we will not be able to explain. And we got a long wavelength cutoff because the total universe around us, at the CMB epoch, not all wavelengths are observable. So it turns out that when you put it in numbers as to which modes are available, so there is a cutoff for the wave numbers. There is a cutoff at the lower end, which is the highest, longest wavelengths, and for and then at the upper end for the wave numbers, which will be the smallest wavelength. Okay? There is a cutoff there like that. And K star is just a fiducial co-moving scale that is always used to understand the data. So one just puts it by hand, so to say. And roughly speaking, from about 0.1 K star to about 300 K star. So what is K star? Well, K star is about 2 times 10 to the minus 3 times megaparsec universe. That is to say, it corresponds to a wavelength of about 10 to the 3 megaparsec here. And this is the pivot or reference wave number used in WMAP. The Planck nation uses some other wave number, but one just converts the results from one wave number to the other, just to, you know. So this is the radius of the radius of the observable cosmic microwave background. So this K star is about 10 times lambda star is the radius of the observable cosmic microwave background. Therefore, if I take the wave number, it is about 0.1 K star. Okay, just. And then finally, soon after the mode exits the Hubble radius, I will explain what this means. Its quantum fluctuations can be regarded as a classical perturbation and evolved using linearized Einstein theory. So I have to explain what this means. So I got this universe which is undergoing a very rapid, nearly exponential expansion. And there are all these quantum fluctuations. And these fluctuations are in a certain vacuum state, the Bunch-Davies vacuum state, which is picked out by regularity and symmetry of the near de Sitter geometry that I got up here. Now, the statement is that as the universe expands out, right, as the universe expands, then we know that the physical wavelength that goes like a to the t times lambda naught, like lambda, the co-moving wavelength, or if you like, lambda physical at time t upon lambda physical at time t naught is equal to a of t upon a of t naught. So as the universe expands, as the scale factor becomes larger and larger, the co-moving wavelength, lambda naught, does not lambda naught, the co-moving wavelength. This is just constant. This is just because you are just taking Fourier transform with respect to some fiducial metric up here, that is just constant. But the physical wavelength then grows exponentially. The physical wavelength just grows exponentially. On the other hand, we saw last time that we got the wave equation satisfied by this chi, the perturbation thing that we wrote down, chi k was chi double prime plus a squared times a squared upon a squared plus this minus the scalar curvature upon 6. So this is the radius of curvature operating on chi k. And we saw that there is a big difference whether we are going to talk about wave numbers which are much larger than this or wave numbers which are less than this. Now in the beginning of inflation, the wave numbers are all less than the square root of r, or k squared is less than r by 6 up here, which means that so at the beginning of inflation, beginning, the wavelengths are smaller than the curvature radius. So they're all wavelengths are small, curvature is large, and therefore the modes don't really feel the curvature at all, which means that this K physical, this is the K physical up here, in the beginning, K physical is larger than R/6. So this term dominates up here. So in the beginning, when the inflation starts, even though the curvature is large, it is 10 to the minus 12 times Planck curvature. So with respect to Planck curvature, it is small, but as I saw last time, it is really large. It is about 10 to the 60 times the curvature on the horizon of a black hole, solar mass black holes. But nonetheless, these wavelengths are still smaller than the curvature radius, and therefore they just propagate as though they are in flat space. But then the physical wave number, physical wavelength increases, or the physical wave number decreases up here. So at some stage, this term starts dominating. So when K physical squared becomes R/6, that is where one says the mode crosses the Hubble horizon. Okay, so there's a competition. The universe is expanding exponentially, scale factor, and therefore the physical wavelength is also expanding exponentially. But the curvature is not expanding exponentially. Curvature is nearly constant because because remember that the curvature is just given by during inflation, the radius of curvature it just is nearly constant because it's like the zero space-time, and in the zero space-time the curvature is just given by 1 upon h0 squared. So the curvature is really constant, the radius is h0 squared. 1 upon h0 squared, h0 squared. So this is really constant up here. So the curvature radius is constant and wavelength is expanding exponentially. So therefore, time comes when a given mode will meet the Hubble horizon, okay, and then after that, the mode actually feels the curvature and is damped because its behavior changes from oscillatory to exponential up here. So there's that big. So the statement is that when K by A becomes R/6, or the physical wavelength becomes the same as the Hubble radius up here. So the Hubble radius L is equal to 1 upon h0, just for dimensional reasons, no other reason, and therefore this is really this curvature up here is the same as the effective cosmological constant, if you like, in this exponential expansion. Let me just rearrange it because there is no cosmological constant term in Einstein's equation, but it is the stress energy tensor of the scalar field behaves as though the energy density is constant and the pressure is equal to minus the energy density. So there is, if you like, an effective cosmological constant. So that is the effective cosmological constant that we're talking about, and we've got this Hubble radius up here. So the Hubble radius is almost a constant, but the wavelength is expanding exponentially. Therefore, for each mode, that will cross the Hubble radius, Hubble horizon, the Hubble radius up here. It's called Hubble horizon. It's not really a cosmological horizon in any sense. There's just a terminology. It really is a Hubble radius that is actually crossing. So when that happens, dynamic changes. Right? Dynamics are before here. And what one is assuming up here is that once the mode exceeds the Hubble radius, once its wavelength becomes large, then it can be that part of the perturbation can be treated as a classical perturbation and evolved via Leibniz-Einstein's equation. There's a lot of literature about why this assumption is justified. Is it justified, and so on and so forth. I do have clear understanding of it, and the statement is that it is really justified to a great approximation. In other words, the mode is still quantum mechanical, but its behavior is tracked extremely accurately by the classical equations after it exits the Hubble horizon. So this is something that one can write down explicitly. In other words, one can introduce on the classical phase space of cosmological perturbations a certain distribution function and do calculations just using a assuming that the state of the universe is described by the distribution function, calculate all observables, correlation functions, and so on. Or you can actually use the full quantum theory in this particular state, starting with this particular state, and then do calculations. And the two agree with each other extremely well for correlation functions, which will involve products of operators, until the product of operators becomes, the number of operators involved becomes extremely large, right? But in observations, we don't see 1,000-point correlation function. We only see 2-point correlation function, 3-point correlation function. That's what one is now looking at, and maybe per 4-point correlation function, but not more than that. And for these correlation functions, the classical description, quantum description, are extremely close to each other. Okay. So this is the assumption up here. So let me now summarize. The idea is that we're not interested in all modes. We're only interested in certain modes in this region up here, where K star is referring to co-moving pivot mode up here. And I told you the reasons for that. This is what observations will tell us about. Then there are minimal assumptions, which is that in the earlier part of the history of the universe, there is an accelerated, nearly exponential expansion. The Hubble parameter is constant, means it is a nearly exponential expansion. Starting from this phase till the cosmic microwave background era, universe is well described by the Friedmann-Lamith-Roberts-Walker with the linear perturbation. And during inflation, not after inflation, but during inflation, the only matter field is inflaton in a suitable potential. And then at the onset of slow roll, we got these modes in the Bunch-Davis vacuum, at least the modes which are relevant to us, they are in the Bunch-Davis vacuum. In other words, we're not making an assumption about the entire quantum state, we're only making an assumption about quantum state as refers to some mode. Other modes, maybe some other state, the observations don't care about it. That's the idea up here. And then soon after the mode exists, the Hubble radius, it can be treated as classical. So these are the assumptions, and the amazing thing, to me at least, is that these are I'm not saying that these assumptions are obvious, natural, or anything like that. But if you make these assumptions, then quantum field theory in this Friedmann-Lamith-Roberts-Walker space-time and classical general relativity implies that in the CMB there will be some tiny inhomogeneities, and these are observationally confirmed, and then these inhomogeneities grow to give us a large-scale structure of the universe. And therefore all large-scale structure emerge from the vacuum fluctuations, which is an extremely strong statement. Now, the inflationary dynamics. So this is, I'm talking about the background. We already discussed it once, so I'll be a little bit quicker here. Because the Hubble constant is nearly Hubble parameter is nearly constant, during this slow roll inflation, the scale factor expands exponentially, as I explained over here. And thus the space-time metric is approximately given by minus gt squared plus e to the 2h. I call that h naught here, just to emphasize there is a constant. And the metric has a constant scalar curvature, which is given by 2 times h squared, which is what I was writing down up here. That the curvature, scalar curvature, is just given by h naught squared. Right? I mean, in the Ritchie tensor has the information about, the curvature scale is the invariant quantity up here. Now typically one has 60 e-folds from the time t equal to t star. So the point up here is that each mode has a different wavelength or a frequency which changes in time, the physical change. But depending on the value of k, the mode will exit the Hubble radius sooner or later. For example, if I have a mode of some tiny wavelength and Hubble radius is here, it grows exponentially, it will cross the Hubble radius. If the mode is half the wavelength, tiny wavelength, they will also grow exponentially, but it's clear that it's going to cross the Hubble radius little later, right? Because this little thing up here has to grow out to infinity, this little thing has to grow out to the Hubble radius, or half of it has to go to the Hubble radius. So I am going to need a little bit more time for this to become the same as the Hubble radius. Is this clear? So if I got a wavelength of this wavelength and it is growing, and supposing the Hubble radius is the wall, so it's all exponentially growing, so it will hit the Hubble radius at some time. If I got this wavelength and it is also exponentially growing, it will hit the Hubble radius a bit later, right? Because I started out with a small amount. whereas the Hubble radius is almost a constant. So therefore, each Bohr hits the Hubble radius at a slightly different time. Not too much different, but slightly different time. And typically one starts onset of inflation to be the time at which the mode with k equal to k star meets the Hubble horizon. So a ball of radius R0 expands out to a ball of radius 10 to the 60. If R0 is a Hubble radius, then the radius of the if R0 is equal to the Bohr radius, the radius of a hydrogen atom, then at the end of inflation, it expands out to a light year. So I was wrong about galaxy. It is a light year, not a galaxy. The size of the galaxy is a kiloparsec, so it's 1,000 times larger. The Friedmann and scalar field equations governing the dynamics. We have seen this. This is the background space-time. These are the equations that the Hubble parameter square is given by 8 pi g 3 or 8 pi g divided by 3 times the scalar density. The scalar density is the density of the scalar field. The density of the scalar field is a kinetic energy term plus the potential energy term. And then for the scalar field, we have got the Klein-Gordon equation, which is written down here in terms of proper time instead of the conformal time. So this implies, these two equations imply that h dot is about 4 pi times g times phi dot squared. So if h dot is nearly constant, if and only phi dot is nearly constant, right? Phi dot is nearly constant. So the statement is that the kinetic energy is not changing much. That means that the scalar field is rolling down the potential very, very slowly. So that is why we are assuming that is actually a slow rolling reflection of it. If in fact, so the inflaton rolls down the potential very slowly with very small kinetic energy, and that is why the phase of interest is called the slow roll. So during slow roll, the potential is very shallow, and therefore the inflaton rolls down very slowly down the potential up here. So its kinetic energy almost doesn't change. It's very small and it doesn't change, and the potential energy. But anyway, kinetic energy is negligible. Most of the energy is coming from the from the potential energy, and since the inflaton is rolling down very slowly, the potential energy also doesn't change very much, and therefore this h is nearly constant. That is the statement. If the kinetic energy were identically zero, that is to say, if h dot were equal to 0, then phi would be constant. Then the scalar field inflaton would remain, the background would remain constant, and we would have exactly de Sitter space-time. But the point is that this is not exactly, phi dot is not 0. It is small. Basically, it is of the order of 10 to the minus 10 times the kinetic energy is about 10 to the minus 10 times the potential energy, so it's very small, but it's not 0. Therefore, it's not true that h dot is not equal to 0. As you can see here, h dot is negative. This is a positive quantity. H dot is negative. So h is changing very, very slowly. So we don't have exactly exponential expansion. We have a near exponential expansion, slightly slower than the exponential expansion, and that is why we call it a near de Sitter phase. So that is what is happening in the background. So what I have done so far, I told you what the assumption is for the inflation, that there is the inflaton rolling down the potential very slowly, and then Einstein's equation will imply that there is a near exponential expansion. The reason is because the energy density is nearly constant and pressure is nearly equal to minus the energy density. So it's like and that is like an effective cosmological constant, and therefore we've got a nearly exponential expansion. And then what we are seeing is that during that nearly exponential expansion, in fact, it's not exactly exponential. We have it's an approximately exponential expansion. The Hubble parameter is not exactly constant. It is decreasing, but it's decreasing very, very, very slowly. Okay, we saw how it is decreasing just a while ago, because in the last slide we saw that in fact h dot is equal to minus 4 pi g times phi dot squared. This is extremely small quantity, and therefore h dot is also small. It's of the order of 10 to the minus 10, so it is very small. Okay. The slow roll parameters. So to say, but the question is, well, it's not exactly exponential, so what distinguishes it from the exponential decay, like exponential expansion? Well, what distinguishes it is this low roll parameter. So there are two which are most important ones. One is called epsilon, which is the rate of change of the Hubble parameter, so h dot, and then for dimensional reason, one just divides by h squared. So h has dimension of 1 upon time, so h dot is 1 upon time squared, and I divide by h squared, which is also 1 upon time squared, therefore epsilon is dimensionless. And what we are assuming is that this epsilon is very small. Using equations of motion, one can show that this epsilon, this is defined just in terms of geometry, but we can also relate it to what the scalar field is doing using the equations of motion, and up to terms of the order of epsilon squared. The statement is that you can take epsilon sub v, I just defined this quantity, to be the derivative of the potential with respect to scalar field upon the potential whole squared, and the statement is that these two are equal to each other up to terms of the order of epsilon squared. So as we say, Planck data says that epsilon is less than about 10 to the minus 2, so we're ignoring terms of the order of 10 to the minus 4 in this case. The second important Rolle's flow parameter is really h double dot upon 2h dot times h. Again, this is for dimensional reasons, which by equation of motion can also be related to the potentials up to the terms of order of delta squared. So these dimensionless parameters quantify the departure from de Sitter space. See, if these dimensional parameters are 0, if h dot was 0, then we would get exactly de Sitter space. But because it is not equal to 0, we don't get exactly de Sitter space, but we get near de Sitter space. Okay. Had the slow roll parameters been 0, we would have de Sitter space-time, and then the power spectrum would be exactly scale invariant. But because they are small but non-zero, the scalar power spectrum is not exactly scale invariant, and the departures from the scale invariance are coded in a quantity called spectral index. And for some reason, for scalar perturbations, one writes the departure is denoted by ns minus 1, right? Not ns, but ns minus 1. So if ns were equal to 1, then there will be no departure from exact scale invariance, but now there is a small departure from the scale invariance. And so ns is almost equal to 1, but not equal to 1. Now for the longest time, the question was really, is inflation, what is a big deal about inflation? Because very general considerations tell you that the power spectrum is scale invariant. I'm going to explain what that means in a minute. If the power spectrum has some scale invariant meaning, power is the same at all scales. That's what scale invariance means up here. So there are questions about, is inflation necessary? But inflation says that, well, as an inflaton is rolling down the potential, the inflation occurs. But as the inflaton rolls down the potential, h dot is negative. Therefore, epsilon is not equal to 0. Therefore, there will be a departure from the exact power, scale invariance. If it was de Sitter, there is exactly scale invariance, but then inflation says that there is going to be a departure. And the Planck mission, for example, has shown that there is a departure from scale invariance. So scale invariance just means that the power is constant with respect to the wavelengths. And the Planck data has shown that this is not the case, and this has been something that is proved to 7 sigma, so it's a really firm prediction, firm observation. So this naive ideas that it was really just an exponential expansion, we don't need inflation, etc., is not true. And I'm not saying that inflation is the only thing that will do it, but it is something that does it. Okay, thus the assumption in the inflationary scenario is that there is a phase in the early universe where epsilon is much smaller than 1 and delta is much smaller than 1. By much smaller than 1, we mean less than a percent, or about a percent. Okay, now finally Bunch-Lewis vacuum that we already did, so I'll be quick up here. So far we're done discuss the background geometry. Now let us consider perturbations. So what we now want to do is to consider perturbations which are going to be quantum field phi of x, as we did in the class, and its Fourier modes, and later we'll relate them to the scalar and the tensor modes. And then we are seeing that we do not have Poincare invariance, therefore these basis functions have to be replaced by some other basis function. and therefore this is, in place of this, we can use any basis. I'm calling it now QK rather than EK, because I want to relate it to the Mukhanov-Sasaki perturbations. So these are cosmological perturbations rather than abstract perturbations. And then we saw that it should satisfy this equation, and there is a normalization condition it should satisfy. And then if you can choose any basis like that, we saw last time, then we can expand out the field operator in terms of the basis. These are generalizations of positive frequency modes times creation operators, and generalizations of negative frequency modes times the annihilation operator. And again, we postulate a vacuum, which is annihilated by the annihilation operators, and we construct a Fock space, and thus we have a representation, as we saw in detail last time. Now we come to the near de Sitter geometry. So like in Minkowski spacetime, as I just mentioned, as we just saw last time, de Sitter spacetime is a 10-dimensional group of isometries. It is maximally symmetric, and therefore by using the de Sitter group in place of the Poincare group and using the usual regularity conditions, one can select a preferred regular Fock representation of the field operator in which the 2-point function is de Sitter invariant. And we saw this last time, that this is called the Bunch-Davies vacuum. But now, the new point, that during inflation, we only have near de Sitter metric. We don't have exactly de Sitter metric. We can write down what the metric is, calculate explicitly, and see that it is close to de Sitter, but the expansion is slightly slower than the exponential. So we go a couple of e-folds before the t equal to t star, and let h naught be the Hubble parameter at that instant of time. So let's call it that instant of time eta naught. So we go a little bit before t equal to t star, and then we look at this time eta naught. And then we consider the de Sitter metric with that particular value of the cosmological constant, and define the required mode functions, qk, by asking that the initial data at this particular time is the same as the initial data for the Bunch-Davies mode functions for de Sitter spacetime with lambda equal to that. So what I'm saying is just the following, that the geometry is not exactly de Sitter, so we go early enough, and then it is approximately de Sitter, and I just use that value of the cosmological constant and construct the Bunch-Davies vacuum. If you like, that Bunch-Davies vacuum is going to be tailored for that instant of time. Is the idea clear? No. Questions? Is it going too fast? Ask something. Okay. Okay, it's okay. Okay. So the statement is that there's a nearly exponential expansion. So in time, it doesn't look exactly exponential. But I just look at a little segment. I go early enough and look at a little segment. Then it will look nearly exponential there. And then I just use the value of the Hubble parameter there and construct the Bunch-Davies vacuum tailored to that instant of time. This would not be a Bunch-Davies vacuum at a little later instant of time because the Hubble parameter changed. But fortunately, if the slow roll is sufficiently slow, then this difference is small and does not make an impact to observations. So one can calculate, one can say, let me choose the Bunch-Davies vacuum tailored to what the space-time geometry is at a given instant of time or a little bit later during inflation. And you calculate the differences, and one finds that there are differences, of course, but they are negligible compared to the observation error. And so it doesn't really matter where I choose this Bunch-Davies vacuum, so long as I choose it a little bit before, but it doesn't matter exactly where, the onset of inflation, right, where t equal to t star, just before that. So the idea is that, well, it's not exactly de Sitter, but we can pretend as though it is de Sitter as far as the selection of the state is concerned. Once you have chosen the state, in the Heisenberg description, the state is the same. It's the field operators which evolve in time. Therefore, there is a mixing of positive and negative frequencies, and then the correlation functions, the 2-point functions, will depend on time. And that is what we're calculating. So again, these mode functions now are going to be given by exactly what we saw, like the Hankel function, except that now the order of the Hankel function, in the de Sitter case, it was just 3/2. Now it is slightly modified by the slow roll parameter. So it's approximately de Sitter, but not exactly de Sitter. we got this epsilon and delta up here. And you can expand it out explicitly up here. And previously it was just the Hubble parameter. Now it's the Hubble parameter at the time when the more k exceeds the Hubble radius. So previously this was just a constant. Now it is slowly changing. It relates to the k. At what time does the more exceed the Hubble radius? What the value of the Hubble parameter there was. So the point is that we do have these mode functions which at the initial instant of time will agree with the de Sitter vacuum, but as we evolve in time, then these mode functions, they will differ from the exact de Sitter wave functions slowly, and that is what we're looking at up here. So that is where the dynamics is in this slow departure from de Sitter. Okay. Now, where to calculate the power spectrum, because that is what is observed in observation. So let me first look at this equation, because you'll find this everywhere in the books all the time. The power spectrum, this is the power, it has dimensions of energy per unit time. I'm always using units in which C is equal to 1, H bar and G are not equal to 1, but C is equal to 1. So power is really energy per unit time. So that's energy is the same as mass, so it is mass upon time or mass upon length. And it is defined as, you calculate the 2-point function of the more, right, of more k and k prime up here. That 2-point function, as you can imagine, is going to be given by delta k plus k prime. Right? That's what the 2-point function will be. Delta k plus k prime up here. Because k is not equal to k prime, this will be 0. Otherwise, you get delta k plus k prime. And then there's a factor. So times some factor. But one puts this factor as some constant divided by k cube times p phi, and calls this p phi the power spectrum. It does have the correct physical dimensions, but you can think of this as the power spectrum. You can calculate what it is, and it turns out to be precisely h bar k cube. Therefore, this k cube cancels this k cube, and the power is just given by h bar times k cube times qk times the Davis more whole square. So we just saw last time that we got this modes up here, which are qk, Davis modes up here, which evolve in time, and we're now calculating the power spectrum. In the power spectrum, we get this. We just substitute creation and annihilation operators up here. Right? It's not a very profound calculation. We got creation and annihilation operators, substitute the expression for phi up there, and then we'll just obtain what the 2-point function is. That is the delta distribution, and the multiple up here will just involve something involving the mode functions k, which is what you would expect to be the case. Now, the point up here is the following. Physically, this is called the power spectrum because of the following reason. I can just break this up into three trivial parts, h bar k times this times k. So 3 parts of it. This k cube has been divided into 3 parts up here. And there is a physical meaning. H bar k, as you all know, is the energy contained in that mode. Okay? And k up here, you can think of it as being a time interval, 1 upon the time interval, divided by that mode. Right? The wave number is just, so I got a wavelength, and we're putting c equal to 1. So I got a wavelength or wave time, if you like, and the wave number is 1 upon that time. So if you like, the time that is defined by the mode is just given by 1 upon k. Time that is divided by that mode is given by 1 upon k. And therefore k is just 1 upon the time divided by that mode. So what we are calculating is how much energy there is in this mode, that is h bar k, per unit time. But whose time? Well, the time of the mode. And therefore we are just taking it to be k. But we are still left with this factor. And this factor, if you use the Klein-Gordon inner product that we we discussed last time, is precisely the probability that we have this mode qk in this vacuum state. So in this vacuum state is we got this operator up here, so I can take I can take the product of these two operators, phi hat of x prime and eta prime, and I can calculate it. And then the statement is that I will get some probability associated with the vacuum state is, so to say, it has vacuum fluctuations. And how many vacuum fluctuations does it have in any one given mode? The probability of that is encoded in k times q absolute value squared. This k is here just because the Klein-Gordon inner product. Remember, in the physical space-time, the Klein-Gordon inner product has a derivative operator. So when you go to momentum space, that derivative operator becomes k. So these three factors are energy in the mode, probability that that mode is occupied in the vacuum fluctuations, times 1 upon the time interval associated with that mode. So therefore, energy in the mode times probability gives us the energy associated with that mode in the vacuum fluctuations per unit time as defined by that mode. So h bar k, energy h bar k is radiated per unit time as measured by the mode itself. Now, for dimensional reason, the tensor modes and the scalar mode curvature perturbations that I introduced before, which is really related to this Mukhanov-Sasaki variable in a very simple way. This is a curvature perturbation, which is related to Mukhanov-Sasaki variable. We discussed this some time ago. So we got the tensor mode and the Mukhanov-Sasaki variables up here. So the statement is that the tensor mode, in terms of the scale, mathematical scalar field we consider, the tensor mode is just square root of 4 kappa, kappa is just 8 pi g times phi k. That's just for dimensional reasons. This is dimensionless, this has some dimensions, this factor kills those dimensions, and then this is the definition of the scalar mode itself here. So as a result, if I calculate what this is, then what one finds is that the scalar and the tensor product power spectra are given by some factors. So remember, in the last transparency, we saw that these QKs are related to the Hubble parameter at the time is that the mode exits the Hubble horizon and so on. And so the statement is that what appears up here is really the time at which the mode, the value of the Hubble parameter at the time that the mode exists, the Hubble parameter, times this kappa h bar. But the important thing is that for the power spectrum of the scalar mode, we have got epsilon in the denominator, whereas in the power spectrum of the tensor mode, we do not have epsilon in the denominator. Epsilon is a small quantity, and therefore the statement is that because it's a small quantity, that means that the tensor mode power spectrum, apart from numerical factors, you see this is the same numerical factors, this factor 2 is there because of the because there are two tensor modes up here, and this 4 kappa h bar comes from this tensor mode is related to the scalar mode by this particular number up here. So the only difference is really between the two things apart from these factors of 2 is really 1 upon epsilon. Therefore you can see that the scalar power spectrum is enhanced by a factor of 1 upon epsilon compared to the scalar tensor power spectrum. The scalar power spectrum is translated into density or the temperature fluctuations. And so what the various missions measure, COBE first, then Planck, then WMAP, then Planck, what they measure is this temperature fluctuations. So the temperature fluctuations they are measuring is a power in the scalar modes. And we can see that the power of the scalar mode has 1 upon epsilon in it relative to the power of the tensor mode. And that is why, to the present day accuracy, we can measure the tensor modes without any problem, the scalar modes without any problem. So far, we have not seen any tensor modes because one needs much more accuracy here because the epsilon is of the order of 10 to the minus 2, so we need this. So exact number there depends on what inflationary potential you're using. But that is what is happening basically. That is the reason why the scalar to the tensor to the scalar ratio has a factor of epsilon. Therefore, with respect to the scalar modes, the tensor power is suppressed by a factor of about 16 epsilon if you just put all the factors together. And that is why it is so much more difficult to measure the tensor modes. Different photon potentials will give different values of this epsilon, and so we can constrain the potentials by non-observation of tensor modes. If a particular potential gives you epsilon to be to be only 1/10, for example, or only 1/5, then we should have seen it. We should have seen the tensor modes. The fact that we don't see those tensor modes means that potential cannot there. So the point up here is that given a potential, we can calculate what epsilon is using that potential up here, and therefore we can calculate what the value of that epsilon is, and the statement is that you can use those values and the fact that we have not yet seen the tensor modes to put restrictions on the class of potentials that are viable. If the potential were such that epsilon was of the order of 1 or epsilon was of the order of, say, 1/10, then we should have seen it, and we don't see it. So that's why those potentials are disfavored. The potentials for which epsilon is small are favored. I mean, particularly. But people are sort of making more accurate measurements now to see if, in fact, what this tensor power spectrum is going to be. So finally, between observation and theory. So onset of inflation is when a pivot mode equals a curvature radius, the wavelength of the pivot mode equals a curvature radius, or if it exists the Hubble horizon. That is the same terminology. And K star upon A naught. A naught is today's scale factor, so it should be about 0.002 megaparsec minus 1. And so this is for W map, and that is what I used in these lectures. And K naught for Planck is slightly different, but like I said, we can just convert one thing to the other. The idea is that at the beginning of inflation, epsilon, these flow roll parameters are very small. During inflation, they're also small, but they're slightly growing slowly because the Hubble parameter was nearly constant, but h dot was not 0, and therefore this the h dot is not constant. The epsilon and delta parameters are slowly growing, and then as the inflaton, so to say, comes down the bottom of the potential, then the inflaton is coming down quite rapidly, and therefore epsilon grows quite a bit, and then we say that's the end of the slow roll potential. So one conventionally takes epsilon is equal to 1 to be the end of inflation. So what one does is the following. One takes a scalar potential, your favorite potential. So there is for example, m squared, 1/2 m squared phi squared potential. Or there's a potential that was proposed by Starobinsky, which near the bottom looks like 1/2 m squared phi squared, but at the two ends, behaves quite differently. All these potentials have some motivation, which we don't have, unfortunately, time to go through. So you choose your favorite potential, and once you have chosen your favorite potential, you can just go and calculate the power spectrum, right? Because we have the power spectrum up here, where we have the 2-point function, we calculate the power spectrum, where the modes, we just calculate what it is. And then we want to compare it with the experiments. So in experiments, people are measuring the power spectrum, how much power there is per in various wavelengths, and that this power spectrum is parameter. So its theoretical definition is this for the scalar modes. That just was followed from what we did before, and we express this power spectrum by certain ansatz. This is just a convenient ansatz to give us some parameters so that we can fit the data. First is the amplitude, one says, kind of the 0th order amplitude, if you like. And then the amplitude is going to be, the amplitude then is the A of S. And then we got factors which involve the wave number upon K start and Ls minus 1, and then corrections. Let's just look at here. So the statement is that if Ns was equal to 1, so we are de Sitter, then of course this factor would not be there, and this amplitude would be just constant. So in de Sitter space, the power spectrum would not depend on the K at all. It will be just As, and it is constant. And that is why it is scale invariant. It doesn't depend on K at all in de Sitter space. As soon as I got Ns not equal to 1, and Ns was related to the slow roll parameter, then the statement is that if Ns is not equal to 1, then this is going to depend on K. So it's going to either increase with K, or it's going to slowly decrease with K. It would have so it would have one tilt, increasing tilt, or the decreasing tilt. But Planck data sort of rules out Ns equal to 1, to 7 sigma level, as I said. And then it gives us the value of what is AS at this K star. And it also tells us what NS is up here. And NS here is not equal to 1. There is a difference about 0.32, 0.33, 0.33 up here. There is a difference between the 0.030. So, I mean, this is not equal to 1. It is equal to, so there is a 0.04 difference up here. That's what we have here. Since the inflationary theory predicts that the power spectrum is given by this formula, as we just saw before, and NS is given by 1 minus 6 epsilon plus 2 delta. Therefore, in fact, we get some constraints, and that restricts the class of potential that we use. Not very much, but a little bit. And this, I was telling you that two potentials which I use very often are quadratic potential, and then there is the Starobinsky potential. Starobinsky potential is 3m squared upon 32 pi g. So this Starobinsky potential has a form that. So quadratic potential first, it just looks like that, like a harmonic oscillator, except that it is very shallow. I'm just not drawing it accurately. And the Starobinsky potential, at the bottom, it looks like that. But then here it plateaus and becomes constant. And here on the negative values of phi, this is quadratic, and this is Starobinsky. And then it grows exponentially. It's very steep up here. And the slow roll phase here is in this region up here. There's a slow roll phase. And the slow roll phase here, it could be when one is at somewhere here, except that the potential is very flat. So therefore the slow roll phase is very slow up here. So this potential is phenomenologically preferred because it predicts the scalar to the tensor ratio much smaller than the one for the quadratic potential. So the statement is here the following. I mean, this is all lightning. I'll put this on the website so you can go through these notes again in some detail. But the basic idea is the following, that the inflaton is rolling slowly down the potential. As it rolls slowly down the potential, the universe expands nearly exponentially. And then the vacuum state that I give in the early times, the Bunch-Davies vacuum state, I calculate the 2-point function in that vacuum state. In the Heisenberg picture, these operators evolve by the formula that we already had. By this formula, the eta dependence up here, this operator evolves, and therefore the 2-point function change in time. And from the 2-point function, you can calculate the power. And then the statement is that this power is something that we actually measure, and from the spectra, we extract two parameters, the amplitude in the power and the spectral index, the K dependence, the fact that the power spectrum is not flat with respect to K, but changes slightly with respect to K, so we measure that spectral index up here. And then we compare with theory, and the statement is that, of course, it does not determine the theory by any means, because the potential is, there are many potentials which will do this. There are a lot of criticism about inflation because it is not completely deterministic, which we'll see in a minute, and it cannot be completely tested. But the statement is that, as we saw, it makes some small number of assumptions, add a particular potential, predict the power spectrum, and you can check that observationally it is something valuable. So I'll go through this in a minute, but basically my view is summarized very well by something that Jim Peeble, a cosmologist who worked quite a bit on the cosmic wave or microwave background in the very early days, is still very active. So he says that, well, inflation is not a fundamental theory. I think that is exactly right. Inflation is not a fundamental theory. Inflation is rather a framework on which to hang a fundamental theory. In other words, to me, inflation is more like the Bohr atom. It's not a fundamental theory. It makes some assumptions. Bohr atom, the assumption was that, well, in atom, I got the proton and I got the electron. Think of it as a solar system. The electron is just going around, it has its orbits. All our classical concepts are perfectly fine, except I smuggle in a new factor. The new factor is angular momentum is quantized. So treat as though the angular momentum of this thing is given by the orbit is given by nh bar for some reason. Don't ask me why, it's just given by nh bar. And then I can do calculations and I check the energy levels and they work out to be in excellent agreement with the observations. The Rydberg constant comes out, the Balmer series is predicted. So you feel, there is something, it has captured some glimpse of truth up here. Right? So why do we feel that? Because it made a few assumptions, and what we got out of the theory, at least in our subjective judgment, is much more than the assumptions that went into it. It doesn't justify the assumptions by any means, but it says, invites people to say, well, there's something right about this assumption. Is there a more fundamental theory from which these assumptions will actually follow, or will justify this particular procedure? I think the same thing is true about inflation. So inflationary paradigm, it has had very significant success in accounting for the C and B fluctuation, which serve as seeds for large-scale structure. People often begin these inflationary talks by saying that it solves a flatness problem, it solves the horizon problems. Unfortunately, we didn't discuss this, but if you're interested, you can come on Friday and I can explain to you during office hours what these arguments are and why they are really not very good. It doesn't really account for flatness, and does not really solve either of these two problems. However, it actually does explain, does account for the C and B fluctuations, which serve as seeds for large-scale structure. And that is very impressive. But there are many open questions. From particle physics perspective, where from inflaton, there is a single inflaton or multiple inflatons, what is the interaction between them? How are the particles and fields of the standard model created in this inflationary process? The general idea is that at the end of the inflation, the inflaton comes to the bottom of this potential and does some oscillations, and then because of these oscillations, as it oscillates, it actually heats up the universe. In cosmology, one often uses the word reheating, but it's really not reheating, it is just heating, because before that we have zero temperature. It's the same thing as what people call reionization. It's not reionization because there was no previous ionization, it's just ionization. So during this last end of inflation, there is heating, and somehow the hope is that in that heating process, the particles of the standard model were created by some interaction, by some fundamental Lagrangian, but this is still very much subject in progress. It is not something that is sort of anywhere determined. So there are many open questions about inflation. And then there are quantum gravity questions, because in inflation, it's very nice that we can begin very early, very close to the Big Bang. But still, the curvature is about 10 to the minus 12 times the Planck curvature. So from the point of a Planck scale, it's quite late. One would like to start when the curvature was Planck scale and then begin and then see what happens up here. And then classical general relativity would fail. We cannot use quantum field theory in a given curved space-time. We would have to use quantum geometry and perhaps quantum fields or perturbations of this quantum geometry, which are quantum fields which are propagating on this quantum geometry. And this is something that was done here quite a lot. In fact, one of the people who did it, a lot of it is Ivan Aguirre, who is going to give us a talk on Friday in the fundamental theory seminar. So that's interesting things that have come out of all this inflation, going beyond inflation. But that subject is still hot. So basically, the Big Bang singularity is assumed exist in the inflationary models, and therefore it should really be resolved by quantum gravity. And then if it is resolved, then can we extend this inflationary scenario and can actually have a theory which sort of accounts in which the inflationary scenario fits in. In other words, there are many attempts which are going on to actually construct a theory on which to hang this inflationary or theory which can be compatible with this inflationary scenario, from which inflationary scenario springs up. So that is the idea. The idea is that it is successful. It is considered widely as a leading scenario for good reasons. People have a lot of criticisms about them, but neither the successes, such as flatness and horizon problems, nor some of the criticisms are justified. criticisms often suppose that inflation is a fundamental theory. If you remove that and just say it's like the Bohr atom, it is in search of a fundamental theory, it is giving you pointers towards fundamental theory, then many of these criticisms actually just dissolve, they disappear in that case. So, of course, it doesn't solve the problem because we still have to construct this fundamental theory to justify inflation. Just as for hydrogen atom, it is because Pauli and Schrodinger gave us a detailed theory of the hydrogen atom, which was systematic, from which Bohr atom came as an approximation. So similarly, we're seeking a fundamental theory here. Okay. So this is the end of the lectures, and I'll just take any questions.